All right, let's dive into one of the most fundamental ideas in physics. What happens when two things collide head-on in a straight line? Think about 2 billion balls hitting each other. What's amazing is that physics gives us the tools to not just describe what happens, but to predict the outcome with incredible precision.
So that brings us to the big question we're trying to answer today. If you know everything about two objects before they collide, I'm talking their mass and how fast they're going, can you figure out exactly how fast they'll be going the moment after they hit? That's exactly what we're going to break down. Okay, so to get started, we need to lay down some ground rules. See, all collisions basically fall into two main categories, and what separates them is how they deal with the energy of motion or kinetic energy. On one hand, you've got what we call elastic collisions. These are kind of like perfect collisions. The total kinetic energy in the system before the crash is exactly the same as the total kinetic energy after. Then you have inelastic collisions, which honestly are way more common in the real world. In these, some of that kinetic energy gets converted into something else. So, what happens to that so-called lost energy in an inelastic collision? Well, it doesn't just disappear into thin air, it turns into other things. It's the sound of the crash, it's the heat you might feel from the friction, or it's the energy that goes into literally bending or breaking the objects. Think about two train cars latching together. They stick and move as one unit. And you can definitely hear that clang. That's energy conversion in action.
Now, for the rest of this explainer, we're going to focus on the ideal situation, a perfectly elastic collision. By studying this perfect model, we can build a really powerful way to predict what's going to happen. So let's set the stage.
So, picture this. You've got two perfectly smooth spheres. Let's call their masses m1 and m2. Before they hit, they're moving with some initial velocities, which we'll call u1 and u2. After they collide, they shoot off with new, final velocities, v1 and v2. And the key thing here is that all of this, before, during, and after, happens along one single straight line.
So how do we actually figure out those final speeds, v1 and v2? Well, it all comes down to two super important conservation laws. For any one-dimensional elastic collision, these two principles are all you need to know to figure out what happens next.
First up is the conservation of momentum. Now, what this really means in simple terms is that the total amount of oomph or motion in a system stays the same as long as no outside forces mess with it. The equation you see here is just the math way of saying that. The total momentum before the hit is exactly equal to the total momentum after.
The second big rule, and this one is specific to elastic collisions, is the conservation of kinetic energy. Just like with momentum, the total energy of motion before the impact has to equal the total energy of motion after. No energy gets lost as heat or sound in our perfect little system. And this equation, well, it formalizes that perfect energy balance. Now, here's where things get really clever. If we take these two big ideas, these two equations, and do a little bit of algebraic magic, we can come up with something much simpler and, frankly, more useful. Basically, you rearrange both equations, and then you divide the energy one by the momentum one. It sounds complicated, but it lets us cancel a bunch of terms and reveal something really cool about these collisions. And after all that math, you get this beautiful, simple result. U1 minus U2 equals V2 minus V1. This isn't just a bunch of letters, it has a real physical meaning. The left side is how fast the two objects are moving towards each other before they hit, their relative velocity of approach. The right side is how fast they're moving away from each other after they hit, their relative velocity of separation. So in any of these perfect one-dimensional elastic collisions, the speed at which they come together is the exact same speed at which they fly apart.
All right, we've got the theory down. Now let's see how this stuff works in the real world, with a few classic examples. This is where you can really see the physics in action.
First up, what if the two objects that collide have the exact same mass? The result is pretty wild. They literally just swap velocities. So if ball 1 was coming in fast and ball 2 was moving slow, after they hit, ball 1 will be moving slow and ball 2 will be moving fast. A perfect trade.
Let's take that one step further. You've seen this a million times on a pool table, right? Two identical balls, but the second one, the target, is just sitting there, not moving. When the cue ball strikes it head on, what happens? The cue ball stops dead in its tracks, and the second ball shoots forward with the exact velocity the first one had. It's a perfect transfer of motion.
Okay, new scenario. What if something tiny hits something huge that's sitting still? Like think of a tennis ball hitting a brick wall. Our intuition is spot on here, and the physics proves it. The massive wall pretty much doesn't move at all. And the little tennis ball, it just bounces right back with almost the same speed it had to begin with, just going in the opposite direction.
And now let's flip that around. Imagine a massive object, like a truck, hits a tiny stationary object, like a soccer ball. The huge truck just keeps on rolling. Its speed barely changes at all. But that little soccer ball gets launched forward with roughly twice the speed of the truck. This right here is why you really don't want to get hit by a big moving object.
Okay, so we've seen the concepts, we've looked at some cool special cases. Now let's roll up our sleeves and actually crunch some numbers to really lock this all in. All right, here's our problem. We've got a small half-kilogram ball, and it's moving at 4 meters per second. It's about to slam into a much heavier 3.5-kilogram ball that's just sitting there. Our job is to figure out the final velocities of both balls after they collide.
So, how do we tackle this? It's a pretty straightforward process. First, you just identify all the numbers you already know, the masses and the starting velocities. Then, you plug those numbers into the formulas we have for the final velocities, v1 and v2. And finally, you just do the math and calculate the answers. And here's what we get. The final velocity of that first, lighter ball is -3 meters per second. Now that negative sign is super important. It tells us the ball actually bounced backward. It rebounded. And the second, heavier ball? It starts moving forward, but at a slower speed of 1 meter per second. This totally makes sense with what we'd expect to see, right?
So we've spent all this time in the perfect world of elastic collisions. But we all know that in real life, no collision is ever truly perfect. So that leaves us with one last big question to think about. In any real crash, where does all that missing kinetic energy actually go? The answer is all around us. It's in the sound of the impact, the heat generated, and any bending or breaking of the objects. And our idealized models, they give us the perfect foundation to start understanding all of that.